Hello everyone. Today we will talk about the spatial capture-recapture. First I will introduce some principles and later we will run some script to run just one single null model, which means without the covered thread, because I want you have just the minimum instruments to run some model, some simple model. Also because, as we will see in our case with the Pallas cat, that does not happen, but with the Pallas cat, there is rarely we will have a chance to add some environmental or even biological coverage. So let's start again with some concept I introduced in our first class when I introduced the course. The aim of the course is not, of course, to go in deep on the scientific aspect, on the math, because it is not for only for biologists, ecologists, but also just for conservationists that work with the Pallas cat, and that not necessarily must have some specific scientific academic background, and then I guess is maybe too hard go through the math and other aspect that is already difficult to catch for people who has a background. So I just want to explain what is again the principle of the spatial capture-recapture, what is itself the spatial capture-recapture. And later we run, as I say, just a null model, not to go through the meaning of the script, but to try to run together. I will tell you how to prepare the file. I will share with you in the Man Working Group website the file you need to load to run the script in this tutorial together with me, and later just change data I put with your own data and run for your model. Generally, a null model give quite a reliable estimation in spatial capture-recapture. We will go in this detail. I will explain you why. So we can start with our presentation. First, very short presentation. First, define the spatial capture-recapture, the parameters, which are three: the density, the encounter probability, and the activity center. And we will talk about camera trapping and SECR. So the spatial capture-recapture is a method used for estimating population density in abundance across the region of interest. So remember, population density. Yeah, we will have a number, of course, we can extrapolate the number, but that number can be extrapolated only within this region of interest or integration region that we will go more in detail to see what does it mean. So the key difference between the conventional capture-recapture and the spatial capture-recapture model is as heterogeneity, allow for heterogeneity in detectability of individual and capture probability depending on the location. In a few terms, is more flexible. While in the capture-recapture, we need really a random deployment of camera traps or whatever detector with a regular grid. In the spatial capture-recapture, we have a little more flexibility on the sampling. Even, of course, more regular is the sampling, more systematic is better, but anyway, as I say, there is a higher flexibility in the sampling. So the spatial capture-recapture model unified population and landscape ecology by incorporating spatial information associated with individual detection to the population model, and we will go to see what that means. One pattern can be defined by the activity center. So this is the first important parameter of the spatial capture recapture, the activity center. Often confused with home range, but it is not. So let's say this is the snow leopard. We have here a number of snow leopard. Let's say the whole population in this area. For instance, with the 10 snow leopard, and probably each one has his own range. But let's say that here there is the activity center. So the most of movement of the whole population will be within this area. Then, of course, what does it mean? That the probability of encounter, that if we count the detection close to this area, will be higher than detection in this other circle, external one, on the edge. Later, we to understand, of course, in the model, if the leopard moving in a straight line or follow a least cost path through an ecological variable. Let's say here is a plateau and here there is a lake, probably to reach this place, or the zone will go just through this side. But let's think as an easy regular like this, just like this center is here, and more or less with no difference, other leopard detection will be more or less equally from the side and the side, because just getting farther from the activity center, the detection will decrease. In this case, we have the activity center here with the most detection, and more we get farther from a side or another side, which means this and this from the activity center, we'll get less detection. The frequency of detection will decrease. So we can treat somehow the activity center as the mean. And the standard deviation, don't go too much in the math, which is the dispersion of the value, the distance of the value from the mean, which means how the value disperses from this mean to the tail of this curve, like this. So we will say in a standard normal distribution that majority of the value, if the value of sigma is 2 plus 2 or minus 2, we will say that 95% of the observation will fall within this curve, the bell curve, no? Like this bell, is like a bell. So 95% will be within this blue area, and the remaining part in outside of this area. So this area, which is represented from the value of the mean plus or minus 2, which means plus or minus the value of the standard deviation. Okay, that's what I say. So the same is happen here. We know that the 95 observation will fall within this value of sigma. But what happened in our case? What happened is that we know that if we put a camera here, a camera trap here, and then other dispersed farther and farther than here, and we count the number of detection, what we will have will be this, that in the activity center, the frequency of detection will be higher. And farther we go, and less detection we will get. So it will be less. More increase the distance from the activity sensor, and less detection we will have, luckily, right? So what we got to look for is the half normal distribution. Why? because if normal distribution is this, and I remove, and I get this situation, this is just half of the normal distribution. If I get all, just I will get in the other side of the tail. So we are looking for the half normal distribution. Okay, here is the sample with the detector that are camera traps that were more or less regularly decreased the number of detection. But where activity center is really? What is the probability to encounter the target species? No one knows, because we don't know actually if it is here. If this is a mountain, we may think it is here, it is here, it is here. We don't know. So we have to find, at least try to find a value, a reliable value for the activity center. To do this, we use generally the maximum likelihood. Is not the only approach, there is also Bayesian approach, but maximum likelihood is the most widespread approach. So the maximum likelihood estimation is a method that determines the value for the parameters of a model, which I remember are density, encounter probability, and activity center. The parameter value are found such that they maximize the likelihood that the process described the model produced the data were actually assembled. So, assuming spatial capture recapture is the model best describing the process of generating the data, and it has three parameters: density, expected detection number, and or encounter probability, and activity center, we want to know which value of this parameter best fit the data observed. So what does, after all, what the maximum likelihood estimation does? Giving our data, try to find a value that best fit with our data. So the principle is like, let's say, attempt to see which one is the best value fitting with the data observed until find the best one. It's like, I don't know if you use Google Earth. Try to go to Google Earth and find a peak of a mountain. You already see, even in Google Earth, there is snow in some peak. You understand that is more or less the area where you can find the peak. So you, with your cursor, can go to through that peak and see that if I go on the left, it decreases. Then go to the right until increase. Then decrease again. Then I stop in the highest point. Then I know that I go on the northern side, it increase again, until here. Then if I go further, decrease. On the left decrease, on the right decrease, down decrease, then that's it. I found the peak. So that is more or less the principle of maximum likelihood. Find the best value fitting with the model, giving our data. And these are density, then the probability, and sigma, which is the activity center. So once this is clear, another important principle is define the integration region. The integration region is the area over which the software calculates the maximum likelihood of each of the captured individual, generating the detection function of space used around the activity center. What does mean? That if we sample in this area, because our cameras are all within this let's say yellow, orange, I don't know, quadrant, it may happen that probably this snow leopard here will be detected here, or will be detected here, and also this other individual can be detected here, or even here, or maybe even here, and the same in this side. So what we are gonna do actually, we are trying to find a region to avoid that, how to say, to avoid, to exclude this snow leopard. which are not within our camera traps detected. Why? Because we have to be sure that in all this, how to say, calculation, but for the maximum likelihood, no leopard will be excluded among those who can get in our area and have some probability to be detected from our camera. So there is a method to how to say, calculate the integration region, to define the integration region, and it must not be too big because it's a matter of time. Because of course the software had to calculate in a mask an integration region bigger, pixel by pixel. Let's say all this gray slide, and then I got to take edges. From the other side, we have to be sure that the integration region is big enough to get this non-leopard or Pallas cat in our case outside or our minimum convex polygon defined by our camera. So, as we know, for the Pallas cat, we have a good way to identify the individual. In the Pallas cat, the best is the face spot, forehead spot, but also sometimes the stripe, sometimes some specific spot close to the mouth or to the eyes. So that's an important part. Try to be correct as we can, the most as we can, to define the individuals. That's very important because if we don't have a good individual identification, of course, our estimation will be wrong, probably. So try to, when you set the camera, if you are interested to make a population estimation, you should be very careful to set the camera in a way that the identification is facilitated. And so the first step will be start the photo in the PC, identify the target species. Okay, like in our case, the Pallas cat. Just go here. This is the individual one. Okay, if it is the individual one, we have to make a folder with the individual one with all this photo. Later, open other photo. See that this one is different than this, and then we make a photo for individual two, folder for individual 2, and then also the same is for individual 3 and 4, and we had to name the photo if possible so that easily we can identify them. For instance, we can write PC like a Pallas cat 01, PC 02, PC 03, PC 04, and then write the site so that we are sure that it's not the same photo we are referring. And then nothing. Once we have all the detection, we will be able to do the matrix with the capture history that I will show how it is done, where basically we show the identification of the cat, the site where it was detected, the date and the time. So that's it. As I said, create the matrix and run a simple model. That is all we have to do. So now let's start with the RStudio to run a simple model.